Starting with kinematics of uniform circular motion. We want to define what the radian is and express angular displacement in radians. I go to the next page. Just like we have linear displacement, you can also have angular displacement. For instance, if you have a circle of this nature and a particle or an object starts from here and moves to here, starts from a distance here and move to this distance. Let me call here P1 and call here P2. P1 to P2. Okay, so what I'll just do is zoom this out so that it can appear better. So the object starts from P1 and moves to P2. It covers a linear displacement of P1 to P2. A linear displacement. Displacement is distance measured in a specified direction. In other words, it moves from here to here. I will draw that again. From here to here. Covering a linear displacement which is equal to the length of that arc, P1 to P2. At the same time, it is covering an angular displacement. If this is the center of the circle, it's also going to cover an angular displacement of theta. So this theta can be in degree or in radian. That it's best to express the angular displacement in radian. So what I meant is, if this linear displacement from P1 to P2 is S, which is the length of the arc P1 to P2, the angular displacement is theta. Okay, so the relationship between the angular displacement and the linear displacement is what I'm going to give in an equation. But I want to quickly initialize each of these symbols. S stands for linear displacement. While theta stands for angular displacement. In radian measurement, the relationship is, of course, this is the radius r from O to P1, P2, or from O to P1, r. In radian measurement, S is equal to r theta. So linear displacement is equal to radius times angular displacement. R stands for radius. R stands for radius. In other words, whenever an object moves in a circular path or negotiates a circular path, moving from P1 to P2, P1 to P2, it covers a linear displacement S as well as an angular displacement theta. So if it moves a complete cycle, of course, it covers a whole circumference for linear displacement and an angle equal to 360 degrees for angular displacement. All right, let's take this a little further. If we divide both sides by time, or divide through by time, let's call this equation 1. You're going to have, I will draw a line here. We're going to have S over T is equal to R theta over time. S over T is linear speed or linear velocity. So S over T is V. Theta over T is what we call omega, which is angular speed. So V is omega R. Linear speed is equal to angular speed times radius. I can call this equation 2. By the way, this is circular motion. Okay, so we might want to divide again by time. Let's divide this equation 2 by time. Divide again by time. Divide through again by t. and you're going to have v over t is equal to omega r over t. V over t is what we call linear acceleration. Omega over t is angular acceleration because this is speed over time, which is acceleration. So linear speed over time is linear acceleration. Angular speed over time is angular acceleration. And the symbol we use for linear acceleration is a, which is a common symbol you know for acceleration. A is equal to angular acceleration, omega over t is alpha, so alpha r. So you will notice that the relationship between linear quantity and angular quantity is linear quantity is equal to angular quantity times radius. For instance, linear displacement is equal to angular displacement times radius. Linear velocity is equal to angular velocity times radius. Linear acceleration is equal to angular acceleration times radius. So I can call this equation 3. Okay, we can take this further. It can be shown that A is equal to v squared over r. If A is equal to v squared over r, we can develop this further. Remember v from the previous formula we got, v is equal to omega r. So instead of writing A equal to v squared over r, we can actually write omega r all squared over r. And that's going to give us A equal to omega squared r squared over r. And that's we reduce to what? Omega squared r. Now these two equations are very important, so I'm going to highlight them and put them in a box. This first one, we need to take note of them. Let me highlight them and put in a box like this. Also this one, this last one, so I'll just erase it and make it better. So A is equal to omega squared r, So let's put it in a color that can highlight the importance. A is equal to omega squared r. That will be in a box. These are very important formulas we're going to be using. So straight to centripetal force and centripetal acceleration. And centripetal acceleration. Whenever an object is negotiating a circular path, there must be a force that will be required to make that happen. So what I'm saying is, if an object is trying to move around a circle, like the first example we gave, an object trying to move from P1 to P2, it can only happen if there's a force. And the reason is this: if this object is moving anti-clockwise as shown, at every point we can draw a tangent to show the speed at that point. That's the speed at P1. Also the speed at this point is this green one. Now assuming it is moving with a speed of 10 meters per second, so at P1 is 10 meters per second, at P2 is also 10 meters per second, same speed. But you can see that direction is changing every time. So even though the speed is constant, the velocity is not constant. So we can conclude that an object that moves in a circular path has a constant speed but a constantly changing velocity because of the change in direction. So I will just note that an object that moves in a circular path moves at a constantly changing velocity. Right, so it's a constantly changing velocity, although the speed remains constant. The speed remains constant. Why can we conclude that? This is because the direction is constantly changing. And if you can recall, velocity is a vector quantity. Direction is constantly changing. Recall that unlike speed, velocity is a vector quantity, so direction is important. So once there's a change in direction, it has a different value entirely. Recall that unlike speed, velocity is a vector quantity. Which includes both magnitude, which is size, and direction. All right, so very quickly, so that we can round off. Velocity is changing. Velocity is changing. And when velocity changes in a given time, that's acceleration. Remember acceleration A. So we can also recall that A is time rate of change of velocity. Rate of change of velocity with time. So because the velocity is changing with time, there's an acceleration. Therefore, we can conclude that there's an acceleration. Therefore, there's an acceleration. As velocity changes in a given time, there's an acceleration. Now, from Newton's second law, the popular law we know from F equal to ma, if there's an acceleration, there must be a resultant force. By the way, F stands for resultant force. F is resultant force. A is acceleration. And of course, m stands for mass. So if there is an acceleration, there must be a resultant force. That means the object has has a resultant force acting on it. So we can say that as there is an acceleration due to the changing velocity, there must be a force. There must be a resultant force. And resultant force acting on the objects, on the object that is moving in a circular path. In a circular path. Now, this resultant force is directed towards the center, and that's what we call the centripetal force. This resultant force is directed towards the center, is directed towards the center of the circular path. And the resultant force is called centripetal acceleration. And the resultant force, or this resultant force, is called centripetal force. The centripetal force. So in summary, we can now draw the circle again with these forces we've talked about, or force we talked about. So if an object from P1 moves to P2, it covers a linear displacement S, assuming it's moving anticlockwise, and then an angular displacement theta, which is the angle it displaces as it moves from P1 to P2. So the angular displacement is theta. And because direction is changing, even though it is moving at a constant speed, velocity is changing. And because velocity is changing with time, there's an acceleration. And because there's an acceleration from Newton's second law of motion, there's a resultant force. This resultant force is directed towards the center. So we're going to represent the resultant force with a thick yellow line that is directed towards the center. I'm going to use this for it. Okay, so this time around we're going to look at how the circular motion can be applied in practical ways. For instance, if an object starts from P and moves around a circle back to P, it completes a circumference, which is a linear displacement, and then the angular displacement is the entire 360 degrees covered, and the 360 degrees is equivalent to 2 pi rad. So when an object moves around a complete circle or cycle, it completes 2 pi rad angular displacement. And we know that the time taken to make a complete cycle is called 1 period. Period is the time, period T, is the time taken to make one complete cycle. So if period is T, which is the time, and the angular displacement is 2 pi rad, and we know that angular displacement omega is equal to, we know that angular speed, which is omega, is equal to angular displacement divided by time. So we can actually say that omega is equal to 2 pi, which is this, divided by time, which is the period. So omega is 2 pi over t. Alright, so, and we also know that f is equal to 1 over t. Frequency is 1 over period. F stands for frequency. So if we develop that further, we can see that omega is 2 pi over t, which is 2 pi over period, and also equal to 2 pi f. Now these are very important formulas that we're going to be using. Now we've already established in our previous work that the angular acceleration, that's A, is equal to omega squared r. A is equal to omega squared r. That's in our previous recordings. So you will discover that if A is equal to omega squared r, if you substitute for omega in this equation we have here, the enclosed box, you see that angular acceleration is 4 pi squared over t squared r. Alright, you can verify that because angular acceleration is omega squared r, and omega itself is 2 pi over t or 2 pi f. So substituting, you will find that angular acceleration is 4 pi squared over t squared r, which is 4 pi squared f squared r. Interesting. Okay, so we know from Newton's second law that F is equal to ma, and also if we are going to substitute the value of A with omega squared r, we can see that F is equal to omega squared r times m, or m omega squared r, which of course is mv squared over r. So any of these formulas can be used depending on the quantities that are provided. Alright, having said that, I think we can consider a few questions to illustrate this. So I'm going to zoom this in as much as possible, and we look at this question. These are some practice questions to illustrate this. So examples, I can call them examples as follows. And this first one says figure 17.20 shows an aeroplane banking to make a horizontal turn. The aeroplane is traveling at a speed of 75 meters per second. This is the linear speed. And the radius of the turning circle is 80 meters. That is the R we're going to use. Now it says, the first question, question A says, copy the diagram, and on your diagram, draw and label the forces acting on the aeroplane. Okay. I need to say a few things about banking in the case of this aeroplane that is moving. First of all, whenever an aeroplane is moving in the air, it has to provide a lift that will counter the weight. So if this, I'm going to use this diagram to represent the aeroplane. So now the weight acts vertically downward, always weight acts vertically downward. So to counter the weight so that the aeroplane will continue moving at the same altitude without coming down or going up, there needs to be another force which is exactly equal to but opposite in direction to the weight. And that's what we call lift, L. The weight is W. So lift has to be equal to weight for that to happen. However, this can only work if the aeroplane is moving in a straight line. Once the aeroplane wants to negotiate a circular path or turn, there must be a centripetal force. If you have seen our previous recording, you will recall that for an object to move in a circular path or negotiate a circular path or a bend, there must be a centripetal force. A centripetal force is required, and that centripetal force is directed to the center. So this aeroplane in this case is trying to turn, it's trying to turn around a circle of radius 80 meters. So there needs to be a centripetal force. And because of that, the aeroplane needs to bank, and I'm going to explain why it needs to bank. First of all, I'm going to redraw the aeroplane with this shape, and of course this time around is banking. Now the weight still acts vertically downwards, always. Weight acts vertically downwards. This is W. So the weight acts vertically downwards. Now the lift will always be normal to the axis of the plane. So this is the lift, also acting in that direction. What I mean by normal is it should make angle 90 degrees with this. That's a lift. Okay. I think that's basically what we were asked to do in question 6a. Copy the diagram and draw and label the forces acting. So this is the weight acting vertically downward, and this is the lift. So why does the aeroplane need to have its lift tilted to the vertical axis? It's necessary to have it tilted to the vertical axis so that a component of the lift, now I'm going to draw this so that as I'm explaining, you'll be seeing that it must be tilted. I'm going to draw this. I'm going to expand this diagram a bit so that I can include all that. It has to be tilted so that the component of the lift, which of course is tilted this way, will provide the required centripetal force that will help the aeroplane turn. Okay, let me include the weight and all the other forces we have. So the weight acts vertically downwards. Now the aeroplane is now inclined at an angle to the horizontal. This angle should be what we are required to find in the second part of the question. It actually asks us to calculate that angle. Now let's call that angle theta. So we're going to find theta. So we need to find the value of theta here. Now remember, this is the weight, the one shown in blue, and this is the lift, the one shown in green. All right, if you understand your geometry, if you resolve this lift into its components, if we resolve this lift into its components, we're going to have something like this. So let me resolve it into its components. And why do we need to resolve it into its component? Because it is not on the axis of the main force. Okay, so I'm resolving it into its components using these two forces. So this will act this way, this one will act this way, so that here is 90 degrees. All right. If we produce this line, the line of the lift, like this angle must be equal to theta. That's simple geometry. This must be equal to theta, and that means here is also theta, vertically opposite angles. So that's theta. So the components of the lift are this and this. Now, this particular component will counter the weight. So I'm going to show that this component counters the weight. I'm going to write that down. Counters weight. The weight. Just a moment. I'm exceeding my boundary for that notation, so I will just do it here. This component counters weight, Okay, while this other component, I will just label it so I can have enough space, provides the required centripetal force. Provides the centripetal force. All right, beautiful. Okay, so we have that. We have that. Remember, this one counters the weight, and this component counters the weight. In other words, it has to be equal to the weight, so that the object will stay in its altitude. The aeroplane will stay in its altitude while it is still in motion. Now, this other component must provide that required centripetal force, which will keep the aeroplane in a circular path, because the aeroplane needs to move in a circular path. And there's no way you can move in a circular path without a centripetal force. So when the aeroplane was just moving in a straight line, there was no need for a centripetal force like this. All that we required was a lift equal to the weight, so that the aeroplane can maintain the same altitude. But when the aeroplane needs to negotiate a turn, negotiate a bend, or move in a circular path, the lift needs to be tilted. That's why the aeroplane itself has to bank. And so once it banks, the lift is now tilted. So there will be two components of the lift. This component and the other component, as you can see. This component and the other component. All right. Trigonometry, simple trigonometry will show us that this component will be L cos theta, while the other component will be L sin theta. Let me use a different color of marker, blue this time around. L cos, no, that's sine. This sine because it's opposite. L sin theta. That's L sin theta. Alright, so that we can finish this question here, let's use this space. I will complete it in the other page. Let me reduce this so we have enough space to do the work. Show the workings. Alright, so that's that. Remember, L sin theta is a centripetal force, F, which is of course mv squared over r. That's what we established in the previous page. We showed that here, mv squared over r. Just let me zoom in so I can see this better. So L sin theta is mv squared over r, where of course v is a linear speed, m is the mass of the aeroplane, r is the radius of this turning circle. Alright, so, and I also said earlier that there's another component which counters the weight, in other words, balances the weight. So we can say that, by the way, we might want to call this equation 1, this first equation, call it equation 1. And then we establish another equation. The equation that has this component of the lift counterbalancing the weight. Lift equal to this component of the lift equal to the weight. And that is L cos theta is equal to the weight, which is mg. So we can call this second equation equation 2. Let me use a red pen so that it's to be obvious for equations 1 and 2. The first one is equation 1, the second one equation 2. Okay, that's the B part of the equation we are solving. This is actually the A part, which we've shown the forces acting. So the B part is what we are solving, the B part of question number 6. That's this B. Calculate the angle. We're looking for the angle now. We need to find the angle which the aeroplane makes with the horizontal. That's this angle, theta, which happens to be this angle because it's the same as this angle. Alright, so we have L sin theta equal to centripetal force equal to mv squared over r, equation 1. We also have L cos theta equal to weight equals to mg, equation 2. To find theta, that's the angle, to find theta, we need to manipulate the equations, these two equations. One of the ways we can do that is to divide equation 1 by equation 2. There are several things that can be done to solve a simultaneous equation. But the best thing here is to divide equation 1 by equation 2. So I can go to the next page and say that, okay, let me just write it down here. Divide equation 1 by equation 2. Okay, so we're going to have equation 1 is L sine theta. Equation 2 on the left hand, equation 1 on the left hand side is L sine theta. On the right hand side is mv squared over r. Equation 2 on the left hand side is L cos theta. On the right hand side is mg. So we're dividing, we'll go to the next page and do that. Let me create a different frame that we'll use for the next page. Alright, so we go to the next page and do that. So we're going to have, and I think we can share this page into 2 to accommodate all that. So remember, equation 1 is L sine theta is equal to mv squared over r. That's equation 1. And equation 2 is L cos theta is equal to mg, equation 2. So dividing equation 1 by equation 2, we're going to have L sine theta over L cos theta is equal to mv squared over r divided by mg. Don't forget that what we did was to divide equation 1 by equation 2. Divide equation 1 by equation 2. Okay, just a moment. I'll have it neatly written out. So now, some quantities can cross out, like L can cancel out L, M up here can cancel out this M down here. Remember theta, this theta can't cancel out this theta because these two are regarded as a common entity, the same entity, a unit expression. Sine theta is together. Theta is not separate from sine. Alright, so we have L crossing out L, M crossing out M, L crossing out L, M crossing out M. So finally we're going to have sine theta over cos theta. And if you remember your trigonometry identities, not trigonometry identities, yes, trigonometry identities, you will remember that sine theta over cos theta is tan theta. So tan theta is equal to v squared over r divided by g, which is v squared over rg. So we can find theta to be, because we're asked to find the theta, theta will be tan inverse of v squared over rg. Beautiful. So we just impute those values as given in the question. So I'll go back to the question, zoom it in so that we see it properly. We are told that the radius is 80 meters, so r is 80 meters. We can actually indicate it here, that's r. And we are told that v is, the speed is 75 meters per second. So this one is for v, the speed. So rv, I think it's basically what we have. G, of course, in G is always required to be a constant, which is equal to 9.81 meters per second squared. So that's what we're going to use. We have, once again, V is 75 meters per second, R is 80 meters. They are all in SI units. So we go ahead, and of course G is a constant value of this. So let's go to the next and find our theta. So theta, which is tan inverse of, open a bracket, V squared is 75 squared over rg, r is 80, g is 9.81. Okay, we close this bracket, and that will give us, so we have theta to be 82 degrees, approximately 82 degrees. Therefore the angle of bank would be the complementary angle to 82 degrees. If theta is 82 degrees, therefore the angle of banking, which is what we are required to find, that's the angle with which the aeroplane will make with the horizontal. Let me put it that way. Therefore, the angle that the aeroplane will need to make with the horizontal axis will be 90 minus 82. 90 equals 90 minus 82. And that gives us approximately 8 degrees. So the aeroplane has to make an angle of 82 degrees to the horizontal to be able to negotiate the circular track. All right. Lift has to be tilted at an angle to the vertical or at an angle to the horizontal so that two components of the lift will be provided. One component is going to balance the weight. The other component will provide the centripetal force. So this is how you can apply circular motion. We'll be looking at the other examples in our next recording. But before we do that, you can practice some of these questions. Let me zoom them in. I think I can zoom out a bit to reveal or no. Let me zoom out a bit again, a bit again. Okay. It says the orbit of the Earth, mass 6.0 times 10 raised by 24 kilograms, may be assumed to be a circle. I think I need to zoom in to capture all, zoom out to capture all. Okay, may be assumed to be a circle of radius 1.5 times 10 raised by 11 meters with the sun at the center as illustrated. So the question says the time taken for one orbit is 3.2 times 10 raised by 7. Calculate I, the magnitude of the angular velocity of the Earth about the Sun. I, the magnitude of the centripetal force acting on the Earth. So this is the question, the information given, and you'll be required to find all this. Then another question is asking for the definition of a radian. By the way, a radian is defined as length of arc. So theta in radian is basically length of arc, as we've already mentioned, length of arc over radius. Length of arc or arc length over radius. Over radius gives the radian measurement. So length of arc over radius, we've already defined that, just to remind you. So it says a small mass attached to a string, the mass is rotating about a fixed point at P. And it says explain what is meant by angular speed about point P of the mass. Okay, let's turn over. Let's see another question. Remember, this is what this question is about. For number 2, let's set another question over there. So let me zoom it in. Let me zoom out a bit to reveal or say a horizontal plate. Let me zoom it up a bit. Okay. A horizontal plate is free to rotate A horizontal plate is free to rotate about the vertical axis through its center as shown. And it says a small mass m is attached from a distance d. The speed of the rotation of the plate is gradually increased from 0 until the mass is seen to slide off the plate. The maximum frictional force between the plate and the mass is given by this expression, F equal to 0.72 W. And it's asking us weight W is the weight of the mass, m. The distance of d is 35 centimeters. Determine the maximum number of revolutions of the plate per minute for the mass to remain on the plate. Explain your workings. Alright, that's another practice question. In this case, of course, using F, you will need to find the speed v, the linear speed v, and of course, just a hint, you need to find the linear speed, find linear speed v. Remember, F is equal to mv squared over r. F is squared mv squared over r, and r is given as 35 centimeters. That's d, which is the diameter, the radius. So when you find v, find linear speed v, and v is equal to omega r. Omega r is the angular speed. With the angular speed, you can now find the number of revolutions per minute. Angular speed is in rad. So angular speed is like the number of revolutions per second. Angular speed is the number of the angle covered in 1 second. The angular displacement in 1 second. That's angular speed. So when you find W, you can actually find what is required. That's just a simple hint. Angular speed omega is the angle displaced in 1 second, usually in pi. An example is, for instance, if you got 2 pi rad in 1 second, it simply means, or let me even say pi rad in 1 second. It means this angle is covered in 1 second. And pi itself, don't forget that pi, okay, by the way, I said this means pi is covered in 1 second. Pi covered in 1 second. So you can know what will be covered in 1 minute. By the way, pi itself is 180 degrees, because if you remember, in radian measurement, 2 pi rad is equal to 360 degrees. So pi is 180 degrees. So this is just hint. I'm giving you some hints to help you solve this. So assuming you got pi rad per second, this is an assumption, assuming you got this. Assuming you got this, it means pi rad covered in 1 second, or 180 degrees covered in 1 second, pi rad. Covered in 1 second. Okay. By the way, that's angular speed. Angular speed represented by omega. So assuming you got omega to be equal to this, that's an assumption. Assuming we got omega to be equal to pi rad per second, and it simply means pi rad is covered in 1 second, which means 180 degrees covered in 1 second. So you can now find the number of revolutions, which is 360 degrees, that will be covered in 1 minute, simple proportion. So for instance, if 180 degrees is covered in 1 second, 360 degrees will be covered in how many seconds? And then you now know how many minutes it will take to cover a particular number of revolutions, because 1 revolution is 360 degrees. Let me also add, 1 revolution is 360 degrees. 1 revolution is 360 degrees, which is 2 pi. rad. Okay, that's for this question. All of this. Another question similar to this is asking for the definition of a radian. I have defined radian as length of arc over radius. Now a stone of weight 30 Newton is fixed using a glue to one, that's this question, to one end P of a rigid rod CP as shown. It says the rod is rotated about end C so that the stone moves in a vertical circle of radius 85 centimeter. Of course, we must convert this to SI unit, which is meter. Convert to meter. The angular speed omega of the rod is gradually increased from 0 until the glue snaps. The glue fixing the stone snaps when the tension is 18 Newton. That is the centripetal force, just like this one was given. So for the position of the stone, at which for the position, we are asked to find on the dotted circle marked with letter S the position of the stone. Now calculate the angular speed omega. It's similar. It's the same formula you're going to use. You're asked to calculate angular speed. Like I said, you find from F equal to mv squared over r, you find V. You first of all find V. After you have found V, you use this formula V equal to omega r, you find omega. And every other thing you are required to do. So that's a simple hint you can use for this. So every other one will be discussed in subsequent lessons.